My name is Jian from Research Center for Business MEMS and Mechanical Engineering of ASE in Japan. So actually in our center, one of the research topics is MEMS sensors and especially for various network applications. So today I would like to present to you some of our recent results about the assembly and the integration of one of the world's smallest wireless sensor nodes with ultra low power consumption for green sensor networks. So here is the outline of this talk. First, I would like to briefly explain the background of this work and about our green sensor network project. In this project, we have about 16 company members and 3 academic institute members. It's a 4 years project, and this year is the 3rd year of this project. So the target of this work is to develop the system architecture and also the integration technology for the world's smallest wireless sensor node assembly. So we mean the world's smallest sensor node. It not only mean the size of sensor node, but also we try to reduce the power consumption, the production cost, and also the maintenance cost to lowest possibility. Because as you know, we may have thousands of sensor nodes in one network, and we also hope those developed technologies can be used as the platform for future green sensors and green power source evaluation and for some new applications. And I will give some results and discussion, finally summary and some ideas about our future works. As we know, the global air pollution becomes very severe in most of the developing countries. The one reason might be the very fast, rapid growth of the economy, and at the same time, the strong demands on the oil consumption or power consumption, and also the huge number of cars. And from another hand, you can say in most of the developed countries, including in Japan, the power consumption per person is quite huge. So people have to think about the energy cycle or to find new green energy. Another important issue to us is we need to understand what is the most of energy consumed for. So for that purpose, in this project, we aim at developing the revolutionary new MEMS sensors that incorporate various communication functions, including the stand-alone power source and also the ultra low power consumption functions for application in low-cost, layout-free, and maintenance-free green sensor networks to reduce the energy consumption through visibility and also the optimization. Well, this slide shows the basic concept image of the layout-free and maintenance-free green sensor nodes. In these sensor nodes, we include different types of revolutionary MEMS sensors. We call it revolutionary because those sensors should have very low power consumption. For example, the power consumption should be less than 100 microwatts. And we have many company members to develop different types of sensors, including the particle sensors, the IR sensor array to monitor the human activities, the CO2 and the VOC gas sensors, and also the current sensor to monitor the power consumption. And all these sensor nodes include the sensor ASIC and RF module. For this part, I will explain details in next few slides. And also we include stand-alone power source. Compared to the commercial available power source like the solar cell, this developed stand-alone power source has very good specifications, like it works very well under room illumination. For example, the illumination can be less than 300 lux. For example, in this room, I think at the moment the illumination will be around maybe 1,000. So you can imagine that 300 lux means this power source can work well in most of the indoor applications. And also, actually from this year, we tried to demonstrate to the application of this sensor node and sensor network in smart convenience stores, in smart buildings and offices, also in smart factories, including our smart clean room. To reduce the production cost to the power consumption as well as to reduce the size, the most important thing is we need to reduce the number of components. So the first topic, we tried to develop the highly integrated RFSSI. This RFSSI can be used not only for data transmission, but also have some signal processing functions, like we include both analog interface and digital interface to sensors. And also this also has ultra low power consumption. We have even the wake up function that means during sleep mode, the LSI can consume less power than commercial available RFSSI chip, and we can control the power consumption of the sensor by just cut off the power supply by analog switch, and also for the data transmission we have very low power consumption because we reduce the length of the data every time we're sending. And this chip size was about 2.5 by 2.5 millimeter. I think still we have space to reduce the size and also to improve the function of this maybe next step. And then we move to the integration. First, we try to use the traditional PCB technology to make the sensor node. For example, this is the first trial where this temperature and humidity sensor node. The size of the sensor node was about 7 by 7 millimeter. And from this image, you can see it's almost the size limit by using traditional technology. And also in that case, even if we use flexible antenna substrate, it will be no meaning because actually 7 millimeter is too big. Our target anyway, if we can make like 3 millimeter size, with flexible antenna, then you can set up the sensor node everywhere, even to the human body. And then we're just thinking about the candidates for the integration. One idea is to use the spiral pump interconnection technology. By using this technology, we design this kind of three-dimensional structure. And inside PCB, we have two cavities. One cavity is for customized RFSSI Harada chip, and another cavity is used for passive components, including resistors, capacitors, oscillators. Then the thickness of this PCB was about 2 to 2.4 millimeter, and the total number of components inside was about 27 or 28 components. And on top surface, we have electrode pads to sensors, including both analog and digital interface, and also power supply to sensors. On bottom surface, we have electrode pads to antenna and also to power source. And by using this structure, we developed two prototypes. In prototype B, we just include our customized RFSSI Harada, and in prototype A, we use the commercial available RFSSI chip, Takeshi chip, to compare the performance as well as the power consumption of these two prototypes. And this figure, the photo shows the assembling of the sensor node to flexible antenna substrate and also same flexible substrate. Here we have some capacitors used for power supply evaluation. In future, we will remove those capacitors. So for the power consumption of sensor node, first is the measurement results about prototype A is the commercial available packaged RFIC chip. You can see that most of the power is consumed by two parts. First part is the sensor measurement and RFSSI wake up, and the second part is about in the data transmission. It takes about 10 milliseconds to the supply current to about 15 milliampere. And actually the voltage of this supply voltage is about 3 volts. And then the results of the prototype B, we can clearly see that we don't need very high power for the RFSSI wake up, because in this RFSSI there is the MCU inside, so it takes a long time, it takes high current to load the program from memory and also to wake up some functions. But in our RFSSI we don't need, so the current used during wake up is only 15 microampere. And also for data transmission, we reduce the length time from 10 milliseconds to about only 4 milliseconds by shortening the length of the data. From this, we also make some kind of evaluation module. The size is much bigger, it's 4 centimeter, 5 centimeter. But the circuit and components are completely the same as the 3 millimeter module. So from the measurement results, we just confirm that the power consumption of this prototype is actually not so high. For example, if the temperature, the humidity measurement in total time every 1 minute, the average power consumption will be around 200 microwatts. But in that case, the total power consumption can be reduced to maybe only 10 to 20% of this prototype A. And also we confirmed that this B28 buried bump interconnection technology is quite efficient for the super compact sensor node assembly, especially the performance, and also we don't see any additional power consumption by using this assembly method. Well, it shows the measured results by using commercial available solar cell. You can say for the outdoor applications, even under very heavy cloudy day, we still collect some data every 1 minute, 100 million data. And if we include the rechargeable battery, I mean, in that case, the solar cell just charge the rechargeable battery, and this battery supply power to the node. We can have the 24 hours continuously working node when the sunshine is good enough during daytime. And this summarizes some of the results. For example, if we use a solar cell 3 centimeter by 6 centimeter, the lower working limit could be about 3,000 lux, but if we change to this solar cell is specially designed for indoor applications. The lower working limit can be as low as 1,006 lux, but actually it's still a little bit high. Actually, in last week, I received our project to develop the standalone power source. I already confirmed that under maybe 500 lux, it still works very good. So in near future, I will also evaluate our project developed standalone power source. And also this is about the performance of the flexible antenna. Okay, so in office we have confirmed that the communication distance can be up to 30 meters. And in very noisy and open space like the MEMS and nanotechnology exhibition, which was held in Tokyo in this summer, they just confirmed the communication distance can be around 12 meters or even maybe longer if we change the antenna, receiver antenna to the high gain receiver antenna. Well, for conclusions, I think I don't have time to repeat, but for future works, we would like to include also our project to develop MEMS sensors and standalone power source to demonstrate some functions of the green sensor network. So actually, our project has already set up sensor network in convenience stores like 7-Eleven with 2,000 stores in Japan. So we would like to continue this demonstration and to also evaluate the system. And also in near future, we will develop the all-in-one type of wireless system node by including the chip antenna and also the power harvesting devices, which is expected to be used in extreme and other environments. Thank you for your attention.